All right, I want to talk about compaction and in a little more detail than what we covered in soil mechanics, but let's look at the compaction curve and the end result of our compaction tests is the compaction curve, which is this. What are the axes? Gamma D after compaction density. In other words, it's the density after we've compacted the soil in the lab. X-axis is water content. If you remember how the test is run, we prepare 5 samples in this particular case. 1, 2, 3, 4, 5. How do we prepare the samples? We take the soil and we put the soil into a mold. So for this particular point, I put the soil into this mold and I compact it using a number of layers and a hammer. So if I do the standard Proctor test, what do? I put the soil down here and for the first layer, and I take a 5.5 pound hammer, I put on 25 blows, dropping the hammer 12 inches. I do that for 3 layers. I then get a density from this and a water content. I put that value on my plot after I've compacted it. Now then what do? Then I take the same soil, but I wet it a little bit. I change the water content. And I repeat the procedure, 3 layers. I get another density, but at a higher water content, so I'm over here. I then change the water content again. Same type of soil, or from the same original soil source. Compact the 3 layers, get another density out of it. Increase the water content some more, do the same thing, get another density. Increase the water content some more, get another density. Remember, this is the dry density. So I then take and create a curve based on my results. That is the compaction curve. It's done in the lab. Now, what do I get out of that? I get the maximum dry density and I get an optimum water content. In other words, I learn one of the main things, what water content should I have this soil at such that I can easily get a high density out of it. That's what I want. So that when this is done in the field, we can get a good density out of it pretty easily. Now, what I just ran was the standard Proctor test. I could run the modified Proctor test, which is 25 blows, 5 layers with a 10-pound hammer. Notice, completely different in the sense, here's 3 layers, I do 5 layers. Instead of a 5.5 pound hammer, I'm going to use a 10-pound hammer. I use 25 blows in both cases, but here I have only a 12-inch drop, here I have an 18-inch drop. So I'm going to get, you can imagine, I'm going to get higher densities with the modified Proctor. So I might have this curve for the standard Proctor, or say this curve for the standard Proctor, but when I do the modified Proctor on the same soil, I get a different result, I get a different curve. So whenever we refer to the gamma D max, I have to really reference my test type. So I shouldn't just write gamma D max, I should write gamma D max and the test type. And so there's also the AASHTO and the modified AASHTO. So they're all just variations in number of layers and hammer blows and that sort of thing. So I'm not going to go through all those, but I just want to make the point that we need to, gamma D max modified, we need to specify that, and it is greater than gamma D max standard Proctor. When we're all done, what we're interested in is what is the relative compaction in the field. RC, relative compaction. What is it? The gamma D in situ in the field divided by our gamma D max. And it would be the standard or modified, for instance. And so what we say is, for instance, in the field, we may have 95% relative compaction, modified Proctor. So we can get this, gamma D max, modified gamma D max standard based on our test in the lab, and then we use the lab test to tell us how are we doing in the field. And we usually have it as a percentage. Now, there's one other gamma D max, and I'll call it the gamma D absolute max for the water content. Now, what does that mean? Well, the soil is compacted fully when the voids are so small that only water is left. In other words, we have water in the voids. If we compact it so much that there's no air left, in other words, that's the best we can do. We can't, we're not going to squeeze out the water. I mean, we could, but we don't want to talk about that. We're just going to say we compact it so much that the water is completely filling all the voids. That means what? The saturation is 1. S equals 1. And if you remember our expression, S times E is equal to G sub S times W. If S is 1, then that means E is equal to G sub S times W. And we know that our other equation was gamma D is equal to G sub S gamma W over 1 plus E. Well, E is equal to G sub S times W, so I put that in there. And I can get the absolute max for my water content by calculating its value using that formula. So you can see we've got 3 gamma D maxes: gamma D max, gamma D absolute max, gamma D maximum for modified, gamma D maximum standard, and like I say, we've also got the AASHTO, modified AASHTO, standard AASHTO. So we got a bunch of gamma D maxes, and whenever we talk about gamma D max, to be understandable, we have to refer to what gamma D max are we talking about. Okay. So here's a little exercise that you should do. Suppose I have a soil in the field where the unit weight is 114.7 pounds per cubic foot. The water content is 16.5%. G sub S is 2.7. This is what's going on in the field. So I've got that soil, I've measured the density in the field, the water content in the field, and I know the GS for that particular soil. And I've run a lab test on this same soil, and here's my lab test. I do my 5 specimens, and at the end of compacting them, standard Proctor, or I should say this is the standard Proctor test. So let's just indicate that is the standard Proctor. And the results are these. We have my gammas and my water contents. Now, what you need to do is find the gamma D, because gamma D is what we plot. So what I want you to do is to basically fill out this table. So I'll just write it here. So we have gamma D. So fill out these values in the right here using this formula, and then plot them, get your compaction curve, which is gamma D versus water content, and then we're going to have 5 points. I don't know what it's going to look like. We're going to get a curve. You're going to get the gamma D max, the optimum water content, and then you're going to get the relative compaction, because we're going to use this value and this value here to get the relative compaction. And then I want you to get the gamma D maximum possible at a water content of 16.5%. And the required is that we want 95% relative compaction in the field, and we want the water content in the field, this one, to be between the optimum plus 1.5% and the optimum minus 1.5%. So to pass, this is required for passing, needed to pass. And I want you to figure out whether or not our soil in the field passes. This is our specifications. You're in the field, you're checking it out, so I want you to figure out whether or not the soil in the field is compacted enough. If it's not compacted enough, then you have to tell the contractor to compact it some more, or remove it and try again. So pause the video here and do this problem. Okay, assuming that you've done this problem, here's the solution. Well, I'm going to use my equation that gamma D is gamma over 1 plus W, and I get my gamma D's here. So for the first one, it's 120 divided by 1 plus 0.102. That's 10. This is in percent. So that's 10.2, so that's 0.102. And I use that formula, I get all of these values for gamma D. So I have gamma D, I have small w, the water content. I can then plot these, and here are my 5 points. If I plot them, I find that this one is approximately the maximum, and that's 113 pounds per cubic foot. And this is approximately my optimum water content, which is 14.1%. Then I find my in situ dry density, which is, again, using the same formula, gamma over 1 plus W. So I get that my in situ dry density is 98.5 pounds per cubic foot. So my relative compaction is going to be the 98.5 divided by the 113, and that gives me 0.871, which is 87.1%. And this is not right. This is the standard. We said we plotted the standard. So let's change that. And so what do we find? That 87.1%, that's less than our 95%, so it doesn't pass. And then we want to know, well, what is the gamma D absolute max? That should read absolute max. Let me just absolute max is this, and we apply our equation G sub S gamma W of 1 plus WGS. I get the maximum possible is 116 0.6, and that would mean that we would need, to reach that, we would have a relative compaction of 103%. So we're not going to get there, but likely, you have to work pretty hard at it to get that in the field. But and then does our water content pass? So if we want to know what that is, our water content in the field was 16.5%, and our optimum water content is 14.1%. So we figure out what is the water content optimum minus 1.5. That's 12.6%. W optimum plus 1.5 becomes 15.6%, but our water content is 16.5%, so it's not in that range between those two values, so not in the range. So we fail on both counts. Our relative compaction was 87.1%, it's less than 95. The water content is not in the range. This soil fails, and so you tell the contractor, okay, you decide what to do about it. Actually, you don't tell the contractor what to do. You just tell the contractor it either passes or fails. Let the contractor figure out what to do about it. And that's the way it's typically done. You don't give instructions. It's their job to figure out what to do. You just don't approve it. So, okay, the borrow pit problem we have done before. I'm just going to review it real quickly. Suppose I have, the borrow pit problem is what? We're creating a fill, and we're taking the soil from a particular location called the borrow pit, and we're going to create the fill. And what we find, of course, is that the volume of the soil taken from the borrow pit is not the same as the volume of the fill. Why? Because generally the soil is less dense in the ground than what we want for the fill. So generally we need to take a greater volume of a borrow pit to create the fill. And a lot of times what we want to know is what volume do I need, for instance. There are different problems that can be created from this. But here's the problem here, and that is that at the borrow pit, this is the situation of the soil. The unit weight is 120 pounds per cubic foot. The water content is 10%. We want to know what is the volume. For the fill, we know the volume here for the fill. We want to build a 100,000 cubic yard fill. We want a 95% relative compaction, and we want the water content to be approximately at the optimum water content. We've run a standard Proctor lab test. We found that gamma D max is 122 pounds per cubic feet, and the optimum water content is 0.15, 15%. So what we want to do is find what is the volume of the pit that we need. How much water do we need in weight to get to the optimum water content in the fill? So notice this is at 10%, this is at 15%. So, okay. So what we need to do is, I'm going to give you a hint on how to do this. First, you need to find the gamma D in the borrow pit. You need to find the gamma D for the fill, and this is using this equation here and this equation here. So we're going to use both of these equations. So okay, so we're also going to use the equation that the water content is weight of the water or weight of the solid. So what I want you to do is to solve this, pause the video, try to solve this problem, and you need to use one other factor. And that is that the weight of the solids here is equal to the weight of the solids here. So that is what joins these two problems together. So you're going to get, so what you should do, so I'm going to give you a hint on how to do this, is to find the weight of the solids in the fill that are going to be there. Because we have the volume, which is here, and you need to get the gamma D. So you take your gamma D max and you're to multiply by 0.95, so you take those two there, and that's going to go in here. So you're going to know two things in this expression here, and you're going to solve for the weight of the solids that you need. Then what you're going to do is you're going to get the gamma D over here using this expression. And then you're going to apply this into this expression, but now we're going to know the gamma D and the weight of the solids. We're going to know those two things, and you need to then solve for the volume. Okay, so there's your hint on how to do this problem, but pause the video and see if you can do this one. Okay, so here's the solution, and what do we find out? Well, in the borrow pit, the gamma D is going to be the gamma over the 1 plus the water content. So the gamma D in the borrow pit is 109.1 pounds per cubic foot. So that's that expression. In the fill, we want to get, the 0.95 times the 122 gives us 115.9. And we know the volume of the fill. Now we know the gamma D. So we solve for the weight of the solids. It's 115.9 times the volume of the fill. Now there's a little bit of a trick here. You got to convert cubic yards to cubic feet. So you multiply by 27, and we end up that the weight of the solids is 3.13 times 10 to the 8th pounds. And then now that we know the weight of the solids, we can solve for the volume of the pit. And we get the volume of the pit is, works out to be 106,000 cubic yards. So we need 100,000 cubic yards for our fill. That means we have to take 106,000 cubic yards from our pit. You may have gotten it in feet. And now, what about the water content? Well, the water content in the pit is just 10%. We want the water content in the fill 15%. So we need to add water to it. And again, weight of the water over weight of the solids in the fill. We know the weight of the solids in the fill. And so we can solve for the weight of the water in the fill. It comes out to be that. And then we can figure out the weight of the water in the pit because, using the same expression. And we get that for the weight of the water in the pit. How much water do we have to add? Well, it's the difference between those two we have to add. So we subtract off those values, means we have to add that many pounds of water, and you can convert that to gallons, for instance. Okay, we just covered relative compaction, but there's another thing that we don't go through in a lot of detail, something called relative density. Relative density and relative compaction are completely different. The symbol for relative density, first of all, is d sub r. The symbol for relative compaction is rc. So, and they are not the same, and you don't want to get confused about these two. Completely different definitions. First thing is we use relative compaction for compacting fill. That's typical what we do. Relative density is usually used for liquefaction problems. So that is the difference, but you need to know relative density also. E, of course, is void ratio, which is volume of voids over volume of the solids. And by definition, the relative density is maximum void ratio minus in situ void ratio divided by the maximum void ratio minus the minimum void ratio. Okay, what does that mean? Now this comes, and there's well, what does that mean? First of all, you have to think about void ratio, volume of the voids over the volume of the solids. When is the void ratio big? That means there's a lot of void volume. If the soil has a lot of void volume, it means it's loose. So we're talking about sands and gravels here. So we can have loose sand, loose gravel, dense gravel. So when we have loose sand, we have large voids. When we have dense sand, we have small voids. When we have loose gravel, we have big voids. When we have dense gravel, we have small voids. So this Emax is when the soil is loose. Emin is when the soil is dense. And so if we look at this denominator, that's the loosest condition minus the densest condition. So we're looking at the difference in void ratio between the loosest and densest. In the numerator, we have the soil in its loosest condition minus what it actually is in the field. So this is the in situ one. So like I say, Emax is the loose, very loose condition. The loosest, Emin is the densest. Now, so when we do the relative density test, essentially, we make it as loose as we possibly can. We make it as dense as we possibly can. So it's not, now I'm simplifying it a little bit, but there are some ASTM rules on exactly how you do this, but pretty much that. So in other words, when we're getting the soil dense, for this test, for the relative density test, it's not like the compaction test where we have these layers and we drop the hammer and all that stuff. We're basically, vibrating it, for instance, and getting it as dense as we possibly can get it. And when we get it as loose, we sort of fluff it up, like you fluff up a pillow. You know how you sort of fluff up a pillow? You can make the pillow really loose and big. That's what we do to the sand, for instance, or the gravel. So that's how we get it into very loose condition. And then we get it into the very dense condition. So now that means that we have another. If we do some conversions here, we find that that these two equations are equivalent. And if I look closely, this is 1 over gamma d min RD is relative density, okay, for relative density, over 1 over gamma d in situ. Gamma d min for the relative density, 1 to gamma d max for the relative density. So, in other words, doing the gamma d min and gamma d max using our relative density procedures as opposed to our compaction procedures. So the way that this works, if I look at this relative density term, what do I have? Well, if my in situ soil is the densest it can possibly be, meaning that this is at E min, what is the value of d sub r? Well, d sub r is going to be what? It's going to be 1, because if this is E min, then the numerator and denominator are the same. I get dr is equal to 1. That's my densest situation. In other words, E min, the minimum void ratio, is the densest. On the other hand, if this is the loosest condition, and that is E max, well, then what's my numerator? Well, then my numerator becomes 0. So what we find is that when it's in the loosest condition, we have a relative density of 0. When it's in the densest condition, the relative density is 1. And if we're in between, so for instance, if the relative density is what we call 50% or 0.5, then we're halfway between the loosest and densest condition. So that is the meaning of relative density, completely different from relative compaction. So with relative density, our values are between 0 and 1. And we often express them in percent. We express it in percent. So 50%, for instance, is halfway between. Okay, so suppose we have a clean sand. Clean sand means what? Not many fines. And for our particular soil, we've done a lab test. We found E max of 0.86, an E min of 0.43, and we have a GS of 2.66. What I want you to do is find E to create a relative density of 56%, and find gamma if the water content is 7% and we have a relative density of the 56%. So use our other equation, but to start with, you need to use this expression. So pause the video here and do this problem. Okay, so what do we find? Well, relative density is there's our expression right there, and we've been given our E max and E min, and if relative density is 56%, I set it to be 0.56. I plug in all the values for these that are given. I solve for E, I get 0.62. So void ratio of 0.62 is going to give us a relative density of 56%. Then for the second part of it, I want a gamma at a water content. So now what? So we know that when our relative density is 56%, our E is 0.62. So we know that gamma D is GS times gamma W over 1 plus E from our relationship equations, and we also know that gamma is equal to gamma D times 1 plus W. If I substitute this into here, then I get that gamma is equal to GS gamma W times 1 plus W over 1 plus E, and I can simply take and I can put these numbers into this expression, and we get that the gamma is 110 pounds per cubic foot. Okay, so suppose when we're working with relative density, for instance, suppose this is what happens. We have a site that might liquefy, for instance. And what do we have to do with that site? We have to get the density to a situation where it's not going to liquefy. So usually we have a relative density target that we're shooting for. So we may have our site that looks like this. Say I have a 6-foot sand layer. I'm afraid it's going to liquefy. It's got a relative density of 40%, a GS of 2.66 at 6 feet, and we're going to use our expression for relative density, and from our lab test we found that E max is 0.9 and E min is 0.46. And I'm going to give you one other equation that I haven't given you before, which is delta H is equal to H delta E over 1 plus E naught. So, in other words, H is the thickness of our layer, and delta H is what? It's the settlement. Delta H is settlement. Settlement. So what we want to know is, well, I'm going to give you this. So what's going to happen is we're going to, delta H is a settlement, or the change in layer thickness is probably a better way to put it. And what we want to do is, first we want to, for this layer, we want to find what the gamma D is, and then we want to find what is the delta H if we increase the relative density to 75%. The relative density is at 40%. We have a target to get it to 75% to prevent liquefaction. In addition, you need to find the E in situ and the E for the relative density of 75%. So pause the video here and do your best to find these values. Okay, so let's start with the first one, which is I want to know what is the void ratio in situ, E max minus E over E max minus E min. I know the relative density is 40%, so I set it to be 0.4. I put in my E max and my E min, and I solve for E. I get 0.724. Then, okay, maybe I didn't say this, the sand is dry here. Yeah, sand is dry. I didn't mention that. Sand is dry. So, what do I know? I know that then gamma, which is GS times SE gamma W over 1 plus E, from our relationship equations from the beginning, then since S is 0 because the sand is dry, that means that gamma is gamma D, which is G sub S times gamma W over 1 plus E. And that means that I just plug in the values here. 2.66 comes from here, 62.4 pounds per cubic foot, we all know that. And then we have our 0.724 as the E, and we get a gamma D for that soil of 96.3 pounds per cubic foot. Then we need to find, so we got that, and we need to find the E for the relative density of 75%. So we do the same calculation that we did up here, but with 75%, we get an E of 0.57. So when we want to use our expression, delta H is H delta E times 1 plus E naught, then our E naught becomes what? 0.724. Why? Because that's what exists in our site before we do any compaction. And then our delta E is going to be the difference between these two. So it starts out at 0.724. We want it to become 0.57. So our delta E is going to be the difference between these two. So let's go there. And that means our delta E is 0.154. I can then look at this expression here. Our H is 6 feet. That's the original layer thickness. The delta E is 0.154. And our E naught is 0.724. I simply multiply that out. I get delta H is 0.536 feet. So that means what? In other words, we want to make sure this layer doesn't liquefy. We have to compact it. And when we do that, we're going to get a settlement of about 1/2 foot. Okay, so that could be a problem for us, and maybe not. But if it's in the middle of nowhere, it's not a problem. But if we have a structure on top of it, that could be a problem. That's likely to be a problem. So, so that is the mechanics of compaction to meet relative density goals for liquefaction. Okay, I'm going to stop there.